Hello Abaqus users, I am Faheem Shah and today I am going to solve a problem from Applied Soil Mechanics with Abaqus application. The problem would be stress is caused by a point load in the soil. Problem statement is that we have a point load of 10 kN which is applied on a soil mass and we need to find the vertical stresses just beneath under the soil, and also we need to find the vertical stresses 0.1 meter apart from the application of load. You can read the problem statement. A vertical point load of 10 kN is applied at the surface of semi-infinite soil mass. Calculate the increase of vertical stress directly under the application of load. For z equal to 0 to z equal to 1 meter, also calculate the increase in vertical stresses at x equal to 0.1 meter, y equal to 0 for z equal to 0 to 1 meter. By using the finite element method and assuming that the soil is linear elastic with elastic modulus value of 10 to the power 7 kPa and Poisson ratio equal to 0.3. As we are interested only in the linear elastic behavior of the soil, we are not interested in elastoplastic behavior of the soil. So we are assuming that the soil is linear elastic in behavior. So we will model the soil as linear elastic, not as elastoplastic material. Let's come towards the geometry. So we have 1 meter by 2 meter geometry. You can see that the right side of the geometry it is constrained in the x direction. The bottom is constrained both in x and y, and the left side is axis symmetric. So we will use x-axis symmetric here, and we will apply point load on the edge of the soil. Let's move toward the next slide. The meshing details. So here we will model two-dimensional axis symmetric finite element mesh. This is very important. Axis symmetric finite element we will use. We need to use 20 elements in the x direction and 40 elements in the z direction. The element chosen is 4 node bilinear axis symmetric quadrilateral elements. These are very important points which I have already highlighted. So keep in mind these points. We will use them in the Abaqus. Results comparison. So this graph is obtained from the SAM HELWANY book, and this is the graph which I have obtained from Abaqus, and you can see the comparison between the results obtained from the book and the results obtained which I obtained from Abaqus. We need to find the stresses in the z direction from 0 to 1. So we will plot the stresses against the depth. Okay, so let's move toward the Abaqus. We are going to model the geometry there. Here in the part module, we need to create the pod. So I will click on create pod. I will name it soil. Here I will select axis symmetric, deformable shell. You can change the approximate size or make it 2, continue. Then I need to click on the rectangular option, select the 0 0 and then 1 comma 2, then click on the done and you have your geometry here. Next step is to obtain the 0.1 meter point from the x-axis. So we need to do partition for that. I will click on tools, then partition, then click on the face, then click on select the sketch option. I will randomly click on 2 points, then I will go to the dimension. I will find the dimensions between these 2 points, which is 0.17 meter, and I need 0.1 meter, so I will enter 0.1 meter. Done. And I will then create partition. You can see the partition has been done. Now we need to move to the property module. In the property module, I will click on the create material, edit material. I will name it soil. We need to define the mechanical. We need to go to the mechanical, then mechanical elasticity, select elastic, young modulus. As we know that it was 1 e to the power 10. I am keeping the unit in Newton per meter, so Poisson ratio was 0.3. Isotropic, okay, done. Then I need to create section, soil, solid, homogeneous, continue, material, soil, then assign section, click on the soil, click on done, soil, okay. So we are done with the property module. Next step is go to the assembly module, create an instances, click on this independent mesh, okay. We have created our assembly. Now the next step is the step module. The step module, I will click on create step, name it as a loading step, loading stage, a static journal, continue. I will click on the non-linear analysis, time period I will keep it as 1 second, initial increment I will make it 0.1 and then okay. So we have completed the step module. We need to move towards the load module. In the load module, I will click on create load. I will name it as point load. Here I will select the loading stage, concentrated force, continue, click on this point, done, and then we need to minus 10 e to the power 3 kilopascal. So for the kilo I will put e to the power 3, and we need to click on the OK. Then the boundary conditions, I will select here initial, symmetric, asymmetric, continue, click on the left hand side, OK, and then we need to define the axis symmetric, so OK. Again on the boundary conditions, then click on the displacement rotation, select this line, done, and we need to extend it in the horizontal direction. Again, continue, bottom, press shift and the other portion, done, and we need to extend it in the both x and the y direction. So we are done with the load module. We need to do meshing. For the meshing, as I have already mentioned that we need to define the axis symmetric element 4 node bilinear axis symmetric quadrilateral element. For that, I will click on the assign element type, click on the soil, select the soil, click on done, and then axis stresses, axis symmetric stresses. So I will uncheck the reduce integration. A 4 node bilinear axis symmetric quadrilateral element has been selected, so okay, done. We are done with this stage. Now we have to assign mesh control, select the soil mass, done, quad structure, okay. Now we have to seed the edges, click on the seed edges, select these two edges, done. Number single we need to 20, so I will 20 and vice ratio will keep it as 10, apply, and okay. I'm changing the seed values as I'm I'm doing it in a more finer way. I'm keeping the mesh more finer so that I could get accurate results. Select these edges, continue. I will keep 50, and we need to change the direction of the arrow. So already selected, done, and apply, and okay. Now these two edges, okay, I will number it as let's see 10, 10, not 10, put it is 5. Okay, done, done, and mesh. Okay, you can see that we have meshed the soil. You can check it. Okay, fine. Now let's move toward the job module. Click on job, name it is point load, continue, okay. Then on the job manager, click on submit. Now the analysis has been completed. Now I click on the results, and this you can see the okay. Now we need to find the depth versus vertical stresses for x equal to 0 and y equal to 0. For that we need to create a path. So I will go click on the tools, then go to the path, create path, select nodeless, continue, add before. Okay, let's zoom it. I will select this node, and then this node. Okay, done. Okay, now I have to click on the create XY data. I will select path from here, continue. Okay, so I will select undeformed. You can see I have the only path, so already selected undeformed. Path points include intersection points, and then select frame the last one. Okay, and from here I need to select the vertical stresses. Apply, and okay, I need to plot it. So we have plot it. Okay, and then save it. Save x1. I will say a vertical stresses is in Pascal. As we know that the vertical stresses are in the kilopascal, so we need to divide the stresses by 1000 in order to get it make it kilopascal. So I will click on the XY data, and then I will operate on the XY data, continue. I will select the vertical stresses in Pascal, and I will divide it by 1000. Plot expression and save as KPA vertical stresses kilo Pascal. And okay, now we need to select the date, and we need to click we need to select the data from here and paste it in the Excel sheet. But for that we need to look at the curve. You can see that the depth value is taken from almost 0.1, not from 0. So we will also do that. We need to select points depth. You can see this is the true distance, so 0 point, this from this point we can select is 0.1, and this, so we will select the data from here, Control C, and we will paste it in the Excel sheet. So you can see that these are the depth values, meter, and these are the vertical stresses. In KPA. Control C, Control V. Okay, done it. We need to uh, make these positive, make these value positive. So drag it. Okay, done. Control Shift and download button and make it this. Now I will select Control C and paste it here. Now we need to load these two values. We need to make it in the reverse order. Okay, and the maximum value you can see here is 1, so we will make it 1, and we will bring the horizontal axis to the maximum value. Okay, close. Now click on the horizontal values. Maximum value you can see here is 500. Make it 500 and OK. So we have obtained this plot. Now we have to obtain this curve, which is x equal to 0.1 meter away from the application upload. For that we need to go to the Abaqus. Here we need to define another path, so I will select click tools and then path, and then create on path, continue, add before. Okay, I need to zoom it. You can see that I have divided it into 1, 2, 3, 4, 5 elements. So this is the point 0.1 meter away. You can also know the coordinates of it. To query node, select this node, so you will choose the node and click on this node. You can see that it's the deform shape, so we will click on the undeform, and now let's zoom it. Node, I will select this node. So here you can see the x coordinate is 1, 10 to the power minus 1, so it means 0.1 meter. So this is our point. So we need to create path, tools, path, create path, node list, okay. And before I will select this node and some node over here in the same line. We will select a little bit below so that it would be 0.1 meter. It would be 1 meter below this point. I'll check it. Okay, done. Okay, so we have created the second path. Now we have to click on the XY data, select path from here, continue, and from here we will select the second path, undeformed point, path points, include intersection. Here the last step, and S2 to apply, and okay, now we need to plot. So we have obtained this plot. As we know that the stresses are in Pascal, we need to convert it into the kilopascal. First we need to save this, save as save xy data. Now we need to operate on the xy data, continue, select this, divided by 1000 in order to convert it into the kilopascal. Yes, save it as vertical, and I will write KPA here. Okay, now we need to click on it, edit. You can see that here the values are not started from 0, but it's just below 0, so we will not select the 0, and we will select from here. Continue the Excel sheet. We will control V here. These are the depth values. And these are the vertical stresses. In KPA. In order to make the values positive, and this value is negative, we will delete this value. Okay, and now we will paste these values here. Depth. Now we need to add a curve to the this sheet, so we right click, change, select data. I will add another series for the X data. I will click on select these values, and for the y-axis I will select these values and OK. You can see that another plot has been added to the graph. Now we need to insert after editing. You can see that the Abaqus plot is this one, the blue one, and this red one is the other one, the x equal to 0.1. This is for x equal to 0.0, and you can see that we have obtained the correct plot. So keep watching my videos. Thank you.